Welcome to Homework Lib.
Okay, so we're doing chapter 34, problem 105 here. So it says for a lens with a focal length f, find the smallest distance possible between the object and its real image. So we want to find the minimum of the distance between the object and its real image. So the distance between that is s plus s prime. So that's what we want to minimize here. So let's call our distance function d of s and call this s plus s prime. So we want it to be only depend on s here, but we have this s prime. So let's use our thin lens equation and solve for what s prime is. So s prime can be written as sf over s minus f. So if we rearrange that, then we have d of s, our distance function here, being s plus sf over s minus f. Cool. So we can also simplify this a little bit. So the cool thing is this is equivalent to s squared over s minus f. Awesome. So we get that by adding like terms. So we have s minus f over s minus f plus sf s minus f. And this equals s squared minus sf plus sf all over s minus f. So that's how we get to that. So if our d of s is now just s squared over s minus f, we want to minimize this. So we need to take the derivative with respect to s and set that equal to 0. So we say 0 equals the derivative of this. So we're going to have to use the quotient rule here. So the quotient rule is going to be the derivative of the bottom times the top. So that is s squared minus the derivative of the top times the bottom. And it's given as minus 2sf all over the bottom squared. Cool. So this is our derivative function. We have to set this equal to 0. So if we set this equal to 0, we know these can go away. And now we're left with s squared minus 2sf equals 0. How do we solve this? Well, we factor it to being s times s minus 2f equaling 0. So the solutions here are s equaling 0 or s equaling 2f. But key here is we know that s has to be greater than f. So we can automatically write out this first one. So we know that s here is 2f. So if s is 2f for our minimum, then we're going to have to plug it back into our function here. So let me add a new page here. Let me write out d of s, we said was s squared over s minus f. So now if we know this would be 4f squared at s equals 2f over 2f minus f. This comes to be 4f. Cool. That's it. This is the minimum distance here, 4f. Cool. So part B asks us the graph of d over f versus s over f. Okay. So let's plot d over f is given as S over F times S over S minus F. So if we plot this versus this, we can see that it's just plotting here. Or let's actually rearrange this. So if I want to say x equals S over F and S equals XF, so d over F of x is x times xf over xf minus f. Actually, let's do this. So these f's will cancel out. This is x minus 1. Because this is f times f cancels. So we're left with x squared over x minus 1 is the plot we want to plot here. So let's plot that. So d over f is equaling x squared over x minus 1 with x equaling s over f. So as a function of x and d over f, let's write this out. So it's much easiest to just use a plotting software here, but I'll go ahead and did that before, and I'm going to draw it out here. So we know the top here is at 10, and I'm going to go all the way up to 10 times over here. So here is 1, and we know that s over f can never go below 1, so this is an asymptote here. Okay, so we also found the minimum is at 4f, so this will be our 4f. That's where we know the minimum is. And it's going to do something like, let me rearrange it. It's going to look like that. And we should see that the minimum is exactly at s over f equaling 2 and d over f equaling 4 right here. So this is our 2. And this is what the plot looks like. Just like that. Awesome.